Today we're looking again at static rigid bodies, but we're just going to focus in specifically on one type. And we're going to focus on a peg question. What specifically makes it a peg question is that at least one of its support points, one of its contact points, is not going to be at the end of the static rigid body. So here we can see that this fishing rod is being supported by the ground and the post. And the post is not at the end of the fishing rod. So this would be what I refer to as a peg question. Okay, so let's quickly remind ourselves of the forces that are going to be generated. Firstly, if there's mass, then there's going to be weight, so that would be the first force. If it's uniform, then that's going to be at the middle. We're not guaranteed it's going to be uniform. The context comes from the question. The contact points produce forces. Here we have the normal reaction force at the ground. So it's perpendicular to the ground, and depending whether the ground is rough or smooth, there may be friction here. At the post itself, we also have a normal reaction force. It's perpendicular to the contact that we have with the post or the peg. This rod is contacting the circular peg at a tangent. So S, the reaction force here, is perpendicular to the tangent, which is why we call it the normal reaction force. Once again, there may or may not be friction depending on whether or not the peg is smooth or rough. Once again, the context of the question may place other forces, other objects or particles along this rod, but this is the default basic diagram we should be able to produce. Now, with all static rigid body questions, we are pulling together a lot of skills that we've used so far in our mechanics course. We're using the fact that we know that this is in equilibrium, but it's a static rigid body. That means it's not moving, and it's stationary. If it's stationary, that means that its resultant force in any direction is going to be 0. So, we know we can resolve vertically, and it should equal 0. We can resolve horizontally, it should equal 0. Even taking moments in any direction, the resultant moment should equal 0. We're going to bring in friction, we're going to bring in the coefficient of friction, maximum friction, and limiting equilibrium. All of these concepts and skills are going to need to be at play within the same question. You're going to encounter some meaty questions that are expecting you to be proficient in each of these different concepts and techniques. So let's get into it for today. Let's start with an example of a peg question. Here's the default diagram that we should always expect to see. And for our particular question, here's the diagram we'd have. We're told that there's a uniform rod AB. It has a mass of 80 kilograms. Length is 12 meters. It rests with one end A on rough horizontal ground. And we're told that the rod rests against a smooth peg C, and we know that AC is going to equal 9 meters. The rod is in equilibrium, and there's an angle of 50 degrees from the horizontal. So this is the diagram that we would produce from this context. The first thing we're asked to find is the magnitude of the reaction at C. So we're looking for that reaction force S. We're going to find that by taking moments. So, as we usually do, I'm going to take moments from A, but there is always a reason that I'm taking moments from A. If I take them from A, I can ignore the two forces R and mu R. Any force that goes through the pivot point when we're taking moments is going to have 0 moment. It's going to have 0 turning effect. So it's useful for me to take these from A. If I chose to take moments from B, I would have to consider the force S, the force ATG, the force R, and the force mu R. 4 different forces to consider with multiple unknowns involved. Taking it from A, I eliminate 2 unknowns straight away. Okay, so from A, the first force I want to consider is the ATG. What's the moment produced by the force ATG? So just making the diagram using the force and part of the static rigid body, the perpendicular distance from A to that force is 6 cosine 50. The actual moment produced is 6 cosine 50 multiplied by ATG. That's going to be the clockwise moment. let's look back at the anti-clockwise moment. Well, that's going to come from the force S, and this is the portion of the ladder that gets us to force S. Luckily, this is already perpendicular. We always want the perpendicular distance from A to the force. This is already perpendicular, so we can say that the anti-clockwise moment is 9s. Okay, with some rearranging, we can make S the subject. This is ready for the calculator. 34.3 G, or 336 newtons to 3 significant figures. Part B of the question wants us to find the coefficient of friction between the rod and the ground. So we should be used to the process here. We now want to resolve vertically to find out R and horizontally to find out mu. Let's start with the vertical. Looking at the diagram, we have two vertical forces, but let's not forget the diagonal force, which will have a vertical component. So let's get some components onto our diagram. So these are the three verticals that we're going to use. We can say that R plus the vertical component, and this is going to be S cosine 50. R plus S cosine 50 is going to equal 80G. Rearrange R equals 80G minus S cosine 50, and we have a value for S that we can substitute in. So that gives us R equals 58G, or 568 newtons. Okay, so a similar thing to find mu R. Let's resolve horizontally. These are the two forces and components we're interested in. So the component here is going to equal mu R. So S sine 50 equals mu R. We can rearrange to make mu the subject, and we can substitute the S value that we know and the R value that we know. So 34.3 G sine 50 over 58 G. And once again, we have our coefficient to 3 significant figures, 0.453. So I'm sure you got these words running through your head before I even say them, but this came down to a good, well-labeled, well-annotated diagram. We took moments, we resolved vertically, and we resolved horizontally. A slight difference here, we had to think about using components because we do have a diagonal reaction force in S. But apart from that, relying on a good grasp of the techniques and the concepts that we've been looking at and building up so far in this course. Okay, Bianca, and we're just about finished. But before you move on to some practice questions, let's take a quick look at the specification and exactly what it is that students are expected to be able to show. Exactly what the examiners are anticipating you'll be confident in. While you read through, I want to quickly remind you that it will be sensible for you to come back and watch this video, re-watch this video at a later date. Maybe come back in 2 or 3 weeks or just before an assessment. And as you watch through that second time round, because you've done your practice, a lot of what you go through here should resonate with you much more, and you have a chance to really embed your understanding of the difficult concepts, the ones that I've been flagging up as A star through the video.